So, welcome to chapter 31, where we transition from direct current to alternating current. So, this lecture is or will cover the fundamental principles of AC circuits, so including here the behavior of resistor, capacitors, and inductors in response to sinusoidal voltage sources. So here we will explore a concept such as the phase source, reactance, impedance, resonance, and transformer. So understanding AC circuits is crucial so as they form the backbone of modern power distribution of electronics. So in this chapter, we aim to achieve several key learning goals related to alternating current circuits. So first is we will introduce the concept of phase source as a tool for simplifying the representation and analysis of sinusoidal quantities. And next is how to use the reactance to describe the voltage across a circuit element that carries an alternating current. Third is how to analyze an LRC series circuit with sinusoidal AMFs of different frequency. And what determines the amount of power flowing into or out of the alternating current circuit. And lastly is why transformers are useful and how they work. So alternating current is ubiquitous in modern technology. Unlike direct current, which flows in one direction, alternating current periodically reverse direction. So these characteristics makes AC ideally suited for power generation and distribution over long distances. So the waves from a broadcast station produce an alternating current in the circuits of a radio. So in this chapter, we will address fundamental questions such as how does a radio tune to a particular station, how are AC circuits different from DC circuits, and how do resistors, capacitors, and inductors behave when subjected to a sinusoidal varying voltage source. To mathematically describe AC voltages and currents, we use sinusoidal functions. So a sinusoidal voltage can be represented as V is equal to V cos Wt, where V is the voltage amplitude, the maximum voltage, and small w is equal to 2 pi f, or 2 pi frequency is the angular frequency. So the angular frequency is related to the frequency measured in hertz. By the equation, by the equation, angular frequency is equal to 2 pi f. In the United States and Canada, commercial electric power distribution systems use a frequency of 60 Hz, where the corresponding sinusoidal alternating current can be represented as in the screen presented. So, where the I is the instantaneous current and the big letter I is the current amplitude or the maximum current. Most present-day household and industrial power distribution systems operate with alternating current, where the primary reason for this is the ease with which AC voltage can be stepped up or down using transformers, enabling efficient long-distance power transmission. So any appliance that you plug into a wall outlet using AC An AC source is a device that supplies a sinusoidally varying voltage. So this sinusoidally varying voltage is or the sinusoidal nature is a key to understanding the behavior of AC circuits. Analyzing AC circuits directly using sinusoidal functions can be mathematically cumbersome. To simplify this process, we introduce the concept of phasors. So phasors are it is rotating vectors that represent sinusoidally varying voltages and currents. The length of the phasor corresponds to the amplitude of the sinusoidal quantity, and the angle of the phasor with respect to the horizontal axis represents the phase angle. So here, the phasor rotates counterclockwise with an angular speed equal to the angular frequency of the AC source. So by using phasors, we can transform differential equations into algebraic equations, greatly simplify AC circuits analysis. When dealing with AC circuits, it's often useful to work with root mean square or the RMS values rather than instantaneous or peak values. So the RMS value of a sinusoidal current is defined as the equivalent DC current that would dissipate the same amount of power in a resistor. To calculate the RMS value, we follow this step. First, we graph the instantaneous current over time. Next, we square the instantaneous current at each point in time. Then we calculate the average or the mean value of the squared current over one complete cycle. Finally, we take the square root of that average value. So this gives us the RMS current, which is measures of the effective current in the AC circuit. So for sinusoidal AC sources, the RMS current and the voltage are related to their respective peak. So the values by simple formulas of the RMS current I sub RMS is equal to the peak current I divided by the square root of 2. So similarly, the RMS voltage V sub RMS is equal to the peak of the voltage denoted by big letter V is divided by the square root of 2. So the V sub RMS is equal to V over square root of 2. So for example, a standard wall socket in the US has a voltage that alternates between the positive 170 volts and negative 170 volts. So meaning the voltage amplitude is 170 volts. However, the RMS voltage is 120 volts, which is the value typically quoted for household electricity. So RMS values are used for most AC power calculation because they directly relate to the average power dissipated in the circuit. So let's begin by examining the behavior of a resistor in an AC circuit. So when a resistor is connected to an AC source, the relationship between the voltage and current amplitudes is governed by Ohm's law. So just as in a DC circuit, the voltage amplitude across the resistor, V sub R is equal to the current amplitude through the resistor. So the I sub R multiplied with the resistance is equal to I sub R times the R and A. R. So a crucial point to note is that the resistance is a constant value that does not depend on the frequency of the AC source. So this means that a resistor behaves the same way in an AC circuit as it does in a DC circuit. So at least in terms of the relationship between voltage and the current. So the graphs of current and voltage versus the time for a resistor in an AC circuit reveal an important characteristics. So the current and voltage are in phase. So this means that the peaks and troughs of the current and voltage waveforms occur at the same time. So in other words, when the voltage is at its maximum value, the current is also at its maximum value. So and when the voltage is zero, the current is also zero. So this in-phase relationship is direct consequence of the Ohm's law. So furthermore, the amplitudes of the voltage and current are related in the same way as in a DC circuit. So the phasor diagram provides a concise visual representation of the voltage and current relationship in an AC circuit. So for a resistor, the voltage phasor and the current phasor are alike, so indicating that they are in phase. Both phasors rotate counterclockwise in the same angular frequency, so the length of the voltage phasor represents the voltage amplitude V sub R, and the length of the current phasor represents the current amplitude or the I sub R. So the fact that the phasors are in phase simplifies the analysis of circuits containing only resistors. And now, let's consider the behavior of an inductor in a AC circuit. So, unlike a resistor, the relationship between voltage and current in inductor is not simply governed by Ohm's law. Instead, we introduce the concept of inductive reactance. So, it's denoted by X sub L, and the voltage amplitude across the inductor V sub L is related to the current amplitude through the inductor I sub L. So by the equation, V sub L is equal to I sub L times or multiplied by X sub L. So the inductive reactance is given by X sub L equal to angular frequency L, where W is the angular frequency and L is the inductance. So this means that the inductive reactance increases with both the inductance and frequency of the AC source. So an inductor opposes changes in current, and this opposition is greater at higher frequency. So the graphs of current and voltage versus time for an inductor in an AC circuit reveals a crucial difference compared to resistors. So the voltage and current are not in phase. Instead, the voltage curve leads the current curve by a quarter cycle, which corresponds to 90 degrees or pi over 2 radians. So this means that the voltage reaches its peak value a quarter of a cycle before the current reaches its peak value. So mathematically, if we represent the current as I is equal to I cos or angular frequency time, then the voltage across the inductor can be expressed as V sub L is equal to I I multiplied by angular frequency times L cos Wt plus 90 degree. So this phase difference is fundamental characteristics of inductors in AC circuits, and it is a consequence of the inductor's opposition to changes in current. So the phasor diagram provides a clear visualization of the phase relationship between voltage and current in a inductor. So the voltage phasor leads the current phasor by 90 degrees, and both phasors rotate counterclockwise with the same angular frequency. So the length of the voltage phasor represents the voltage amplitude, or V sub L, and the length of the current phasor represents the current amplitude, I sub L. So here the 90-degree phase difference is a key characteristic of inductors in AC circuits, and it is essential for understanding their behavior and in more complex circuits. And now, let's examine the behavior of capacitor in a AC circuit. So, similar to inductors, the relationship between voltage and current in a capacitor is not simply described by Ohm's law. So, here is we introduce the concept of capacitive reactance. So, it denoted by X sub C. So the voltage amplitude across the capacitor V sub C is related to current amplitude through the capacitor I sub C by the equation of V sub C is equal to I sub C multiplied by X sub C. So here is the capacitance reactance is given by this equation, where the W is the angular frequency and C is the capacitance. So this means that capacitive reactance decreases with both the capacitance and the frequency of the AC source. So a capacitor opposes changes in voltage, and this opposition is weaker at higher frequencies. The phasor diagram provides a complementary visual representation of the voltage and current relationships. In a capacitive AC circuit, here the voltage phasor lags the current phasor by 90 degrees pi over 2 radians. As before, both phasors rotate counterclockwise with the angular frequency of the AC source. So this 90-degree phase lag is a defining characteristic of capacitors in AC circuits, arising from the capacitor's inherent opposition to voltage changes. The length of the voltage phasor corresponds to the voltage amplitude across the capacitor, while the length of the current phasor represents the current amplitude. This graph provides a valuable comparative overview of how the resistance of a resistor and reactance of an inductor and capacitor vary with angular frequency. So here is, as you can see, the horizontal line represents the resistance, or the big letter R, which remains constant regardless of their frequency, while the upward sloping line represents the inductive reactance, as present here as the X sub L, which increases linearly with frequency. Conversely, the downward sloping curve represents the capacitive reactance, or here is X sub C, which decreases inversely with frequency. So this frequency dependence is a key distinction between resistors, inductors, and capacitors in AC circuits. So, at angular frequency is equal to zero in DC circuit, there is no current through a capacitor because a Xc approaches infinity. So, in the limit, angular frequency approaches infinity, where the current through an inductor becomes vanishingly small. The frequency-dependent behavior of resistors, inductors, and capacitors is exploited in numerous applications, so including here the loudspeaker crossover networks. So loudspeakers typically consist of a woofer for too low frequency and a tweeter for the high frequency. So a crossover network is used to route the appropriate frequency range to each speaker. So the capacitor in the tweeter branch blocks low-frequency components but allows high-frequency to pass. So, though ensuring that tweeter only reproduce high-pitched sound. So conversely, and the inductor in the woofer branch blocks high-frequency components but allows low-frequency to pass through. So, ensuring that the woofer only reproduces a low pitch sound. So, this selective routing of frequencies is essential for achieving optimal sound reproduction in a loudspeaker system. And now let's consider the LRC series circuit, so which combines a resistor, an inductor, a capacitor in series with an AC source. So in this case, the relationship between the voltage and current is governed by the impedance, as indicated as letter Z of the circuit. So the impedance is analogous to resistance in a DC circuit, but it takes into account the frequency-dependent reactance of the inductor and the capacitor. So the voltage and the current amplitudes are related by volts is equal to amplitude times the impedance, where V is the voltage amplitude, while the I is the current amplitude and the Z is the impedance. So as you can see here, the formula Z is equal to square root of R squared plus X sub L minus X sub C squared. So here, the phasor diagram for the LRC series circuit provides a valuable tool for visualizing the voltage and current relationships. So in this case, we assume that the inductive reactance or the XL is greater than the capacitive reactance, which is indicated here as a X sub C. So the source voltage phasor is the vector sum of the voltage phasors across the resistor, so inductor and the capacitor. So the inductor voltage phasor leads to the current phasor by 90 degrees, while the capacitor voltage phasor lags the current phasor by 90 degrees. So here is the resistor voltage phasor is in the phase with the current phasor. So all circuit elements have the same current phasor because they are connected in a series circuit. This phasor diagram illustrates the case where the inductive reactance or the XL is less than the capacitive reactance or the XC. So in this scenario, the source voltage phasor lags the current phasor and the phase angle is negative. So the source voltage phasor is still the vector sum of the individual voltage phasors across the resistor, inductor, and capacitor. So the K difference is the relative magnitudes of VL and VC which affect the overall phase angle between the source voltage and the current. Bioelectric impedance analysis is a technique used to estimate body composition, so including body fat percentage. The electrodes attached to the patient's chest apply a small AC voltage of specific frequency. Example here is 50 kHz that the attached instrumentation measures the amplitude and phase angle of the resulting current through the patient's body. These measurements depend on the relative amounts of water and fat along the path followed by the current. Since water is a good conductor and fat is a poor conductor, the impedance of the body is sensitive to body composition. BIA provides a non-invasive and relatively inexpensive method for assessing body fat percentage. Let's now consider the power dissipated in a resistor within an AC circuit. So if the circuit element is pure resistor, the voltage and current are in phase. So the instantaneous power P is equal to VI is always positive, indicating that energy is continuously dissipated by the resistor. So the average power dissipated in the resistor is given by this equation, where V and I are the voltage and current amplitudes respectively. So for the power in an inductor, if the circuit element is pure inductor, the voltage leads to the current by 90 degrees. So the power is negative when V and I have opposite sides. So here is a K in the diagram which represents different different color edge lines, while instantaneous current denoted by I is represented as the purple line curved line across the Cartesian plane. So here is the instantaneous voltage across device or denoted by small letter V represent the light blue curve in the horizontal line across the horizontal line, while the instantaneous power input to device is denoted by small letter p is represents here a black curved line.